Welcome to episode 9 of the Analytically Speaking podcast series. This episode will discuss the world of data analysis used for spectroscopy and other analytical methods. I'm Jerry Workman, the Senior Technical Editor of Spectroscopy and your podcast host. Thanks to our listeners for joining us for a deeper look into all things measured with light. Spectroscopy is the study of the interaction of electromagnetic radiation, commonly referred to as light, with matter. In this episode, we have the pleasure of speaking with Dr. Rasmus Bro, a full professor at the University of Copenhagen and one of the foremost active living data analytics and chemometrics experts. Over the years, he has worked on many aspects of chemometrics, developing numerous algorithms and methods ranging from fuzzy logic, deep learning, analysis of variance, and tensor modeling. He has received numerous awards in chemometrics and in the analytical sciences, and is the second most cited scientist within the field of chemometrics, with nearly 37,000 citations and an H-index of 78. Most of the algorithms and data sets he has worked on have been made publicly available on the internet. We have invited Rasmus to our Analytically Speaking podcast to discuss his research on the development and automation of several chemometrics methods for use with any spectroscopic technique. Well, Rasmus, thank you for joining us today.
And thank you for inviting me. I'm very pleased and honored to be invited here.
Well, that's fantastic. Well, Rasmus, could you tell us, our audience, a little about your history in exploring data analysis and chemometrics?
Yes. So originally, I'm a chemist by training, or a chemical engineer, and my whole education was actually planned towards working with medical devices. I kind of liked mathematics, but I realized that it was sort of useless. Well, that was my opinion until the last year at university, where I heard a 1-hour talk about chemometrics by a guy called Carsten Ritter, who is kind of the founding father here in Denmark for chemometrics. And I was completely sold. And so I skipped everything that I had been studied for years, and I just went for chemometrics. I saw that was where I had to go. And luckily I got a job at the university I'm still at, where my boss was kind enough to let me work with these things. So I've been digging into algorithms since then.
Well, that's very interesting. Would you briefly explain the generalized concept of how chemometrics is used for modeling spectroscopic data?
Right. Well, yes. So I'm in a food department, and we use spectroscopy quite a lot for different kinds of things. The sort of traditional spectroscopic method in chemometrics would be the near-infrared spectroscopy. And some people, I know you, Jerry, are familiar with Carl Norris, one of the founding fathers in that area. He was actually able to sort of use his chemical insight to just pick out the right variables. You know, if he wanted to predict protein or fat or something, he would have enough chemical insight that he could pick the right variables and actually often some ratios of variables, and do classical multiple linear regression. And if everyone had the same insight that he had, well, maybe we wouldn't use the more advanced chemometrics. But what I would say is that the chemometric methods, such as the regression method called PLS, allows us more sort of normal people to actually achieve what an expert like him was able to achieve. So somehow the chemometric methods have brought advanced spectroscopic analysis to a much broader audience, and that's also why it's so widespread today and used in so many different areas. Don't know if I actually answered the question, but
Yes, I think so.
Okay.
And, Rasmus, you've recently automated the analysis of several methods such as parallel factor analysis, that's called ParaFac, and ParaFac2, calibration model fusion using PLS models, and automatically generating hierarchical PLS discriminant analysis models. Could you briefly explain what these methods are and how they can be automated?
Right. Yes. Actually, let me maybe start in another place. as most people are aware, there's currently a hype on machine learning and artificial intelligence, and that's all fine and good. Part of the hype is that these methods are sometimes oversold and sold to people that are then relieved that now I don't have to think about things. I don't have to think about experimental design, sampling errors, analytical quality, etc. And and when that happens, and I'm sure many of the listeners have seen things like that, those projects typically fail because these new and excellent methods don't actually sort of replace the responsibility of you to actually know what you're doing. So that's not the way that you can go about automating things, at least not blindly. But I do believe that we as chemometricians spend a lot of time using our chemical insight on things that are sort of trivial. And so I would like to automate some of the more established problems that we have. Like if you think about NIR calibration models, we've been doing that for 40, 50 years. And in the most sort of trivial circumstances, that shouldn't be something we spend much human resources on. I believe that can be automated. So I've been trying to automate some of the things that I have been working with. If we take Parafac, which is something I have worked a lot on, that's a method that is extremely powerful for analyzing fluorescence, excitation, emission data. And it's complicated to do a Parafac model. You need to be a skilled chemometrician because it's a somewhat complex model. It's what we call a tensor model, and tensors are a little bit scary. But on the other hand, if you have built 1,000 Parafac models of fluorescence data, you get the idea of how you do that. So the real trick, I think, is that if the data is good enough, if it's a standard fluorescence data set, and you would have to define what's a standard fluorescence data set, but if it's a standard fluorescence data set, there's enough samples, they span what you're interested in, it has a reasonable complexity, then the modeling is a fairly trivial thing, and you don't actually need to be an expert to handle that. And in those cases, we are actually able to take the experience of the experienced users and build an algorithm that automates that. And maybe now I got sidetracked a little bit, but this is the background for why we want to do that. And in the examples that you mentioned that we have tried to automate, we use different approaches, and the automations have different levels of maturity, I would say. Some of them are very generic and very broadly applicable. Others are still methods in development. But the basic thing is that anything that feels remotely repetitive should be automated, I think. Just like in good programming, don't repeat yourself. And the same goes with analyzing data. If it feels a little bit repetitive, probably it can be automated. And that's the motivation we had for this. It turns out then, as a bonus, when you do automation and it works well, we often or sometimes find stuff that we were not expecting. So it turns out that the automated methods can sometimes be better than us, and in most cases, at least, much more consistent than we are.
Well, that's a very exciting. You've really answered the question of why we would want to automate chemometric methods, but can you say some things about the advantages and the caveats?
Yes, definitely. So the advantages is, if you talk about, you mentioned Parafac 2, we have tried to automate the use of Parafac 2 for modeling untargeted chromatographic data, gas chromatography, so GCMS, where you typically want to find, it depends, of course, on what you're doing, but you want to find hundreds of chemicals. You want to integrate the peak areas and estimate the pure spectra, identify, etc. This is something that a person would spend days on doing. So people in companies, people in universities are spending days on analyzing one data set, turning the actual measurements into a peak table. That's days of a skilled scientist. And we believe that we can actually automate that completely. It's not perfect, but we believe that it is way better than the manual methods. And in some of the comparisons we have done to our automated methods with these manual methods, we find that people often make mistakes, of course, because it's boring. And so people will often make mistakes along the way when you sit and manually integrate or whatever is the job at hand. You're going to make mistakes. Now, machines are much better at not making mistakes when doing boring stuff. So the advantage is that we get much better quality. We get also, it turns out, often more information out than you would do manually, and it's cheaper because it only costs a computer. Now, the downside is that there's no room for surprises. So the models don't actually handle deviations from whatever you have assumed about the data, and the models are not perfect. But I would say that now you can have an analyst look at the results of this and in 10 minutes figure out would there be any remaining issues. For many of these, I don't actually see a real disadvantage. They're not perfect, any of them, and they don't work for all types of problems. They have assumptions, but when those assumptions are met, I really don't see a reason why you want to do it, let's say, the old-fashioned way.
Oh, how do you really include years of experience in analyzing data into such software automation?
That is a good question. I think it's actually sort of simple. So, meaning, I don't think we are putting a lot of experience in there. We're just putting the pertinent experience in there. So we're not actually. It's not. The models are not very advanced, I would say, but they just have the right kind of experience. So what is really important, like for example, if we talk about the GCMS data, I'm not a GC guy, and we would not be. This is not me who has developed this. This is me and many people, PhD students and others over the years. And I would think that for our GC, we have at least been 10 PhD students working on that. So even though I say it's not a lot of information, it does take a lot of time. That's another thing about these things. I started analyzing fluorescence data 25 years ago with Parafact, and I'm still trying to improve that and make it better. The funding schemes of research nowadays doesn't really take that into account, but these things take time. So it's a refinement where we try to sort of make all the competences take part. So you need to have chromatography. It's not a data analysis job to automate GCMS. You really need to have information about the instrumental, the analytical, and the chemical issues. And only by including all of that and having these people talk to each other, you can do it. But my job is basically to listen to what a chemist is saying and then understand how I can express that mathematically. So when you listen to people complaining about, let's say I build a PLS model and have people complain about that, I can from the complaints understand how can I actually operationalize that mathematically, if that makes sense.
Yes, it does. So you've basically automated the boring aspects so that you can generate a model, but it still requires human interaction and collaboration with domain knowledge. Is that what you're saying?
Yes, absolutely. Without that, there's nothing, and the continued sort of development of this requires a close contact with the domain knowledge. Without that, there's nothing. That's really maybe my main understanding is that without domain knowledge, you're going to waste a lot of time. I think.
Oh, so you're saying that if one uses automated methods, um, possibly they should be avoided by people who have no domain knowledge or real understanding.
Yes. Well, yeah. The thing is, so if My ideal is to develop models that don't speak math but only speak chemistry. I believe that I can analyze chromatographic data in such a way that I only have to visualize things that make sense to an analytical chemist, and therefore the analytical chemist should be able to, complain and be critical about my results, because they don't need to understand about tensors or about component models and things like that. They can actually just look at it and chemically understand what is happening. And in that sense, the methods I try to develop are aimed at the domain owners. Um, Now, it might be that someday you can just use it as a plug and play, but really the critical thing for these methods to work is that someone who is skilled in making a research project or in a factory or whatever, in an industry, understand how to do that. Um, Also as part of this AI deep learning hype, people will go ask you for numbers to fix stuff, and that really doesn't work. You actually have to understand, these things like sampling error. Do I span the right variation? These things, and when that is sort of in place, then these automated methods will work. But an outsider is not able to do that. An outsider is not able to run a chromatographic instrument, for example. You actually need skills to do that. And if you don't have them, the methods we develop are probably not going to work. They assume good data.
Okay, interesting. And you wrote a very interesting and well-known paper entitled "Who is Winning: A Comparison of Humans versus Computers for Calibration Model Building." Could you explain a little about the theme of that paper?
Yeah, that it's a very nice piece of work. It's not me. I was a co-author, but it's Morten Rasmussen who was the main had the main idea. We teach chemometrics at our university to the food scientists, and we have several courses. So we actually have quite a lot. But in this context, we have a basic chemometric course, and we also have a more advanced chemometric course building on that. So what we tried to do was to give students some calibration task, which in our world would be a classical PLS calibration task, spectral calibration task. And we did that to the students following the basic course, quite in the beginning, as I recall it. So they were not very skilled. Then we also gave it to students after taking the advanced course, so they're supposed to be more skilled. And we also gave it to PhD students working in our group. And we gave it to an automated machine learning method for building calibration models. And the result was that if the data is well presented, like a school book example, then you can give it to any monkey, so to speak, and it's going to be fine. There's no problem. But the more difficult the data is, the more critical it is that you have some understanding both of the data and of the data analysis. So we saw that the more experienced you are, the more difference it makes. But there's a lot of data, simple data, where anyone can build a nice model. So we still need the skills, because as anyone working with real problems know, the data normally don't follow the school book examples. But if you do have that kind of data, then you can do whatever, and that's probably also a hint at where my automated methods are working. That's mainly for well curated data, I guess, something like that.
Well, I can note to our listeners that this paper is cited in the references and further reading section for all those who want to look that paper up. So, do you have any warnings to our listeners about applying deep learning or machine learning to chemical problems? And what's the warning when using these powerful modeling methods if the data is sparse?
Hmm. I think maybe I have a more general warning, which is don't do black magic modeling. you do see a lot of bad applications of deep learning, but maybe you even see more bad applications of the use of p-values and stuff like that. Um, and it's all based on the fact that people are using methods they don't really understand. And if you understand what you're doing, if you're experienced in what you're doing, then all of these methods are very fine and very powerful, but you have to know what they're doing, what you're doing. And the problem, maybe with the deep learning, but not solely with that, is that it's being sold as a black box approach. Like you don't have to understand, and people overinterpret that as I don't need to know anything. Give me a DVD with your or a USB with your data, and I'm going to fix your factory. And things don't work like that. So I think my general advice is just to be be skilled in what you're doing. I don't mind if you're doing deep learning or linear regression or lasso or whatever, as long as you know what you're doing and you know the pitfalls, you know what you have to be careful about, I would say.
That sounds like excellent advice. What are some of your all-time favorite software or books or papers covering chemometrics?
Okay, so now I think I'm gonna reveal my age, because the things that made the biggest impact on me was what I was reading initially when I was desperately trying to understand what this PLS model was about, and I really couldn't figure it out. Um, Eventually, I managed, and I would say one of the papers that meant the most for my understanding of PLS was a paper called PLS Regression Method. It was written by Agner Höskulsson in 1988, I believe, and it was for me it was a revelation. Maybe when you read it today, well, actually still today I would say that it's an interesting paper. It presents a lot of insight, but at the time you have to remember that it was not well understood exactly what PLS was doing, but that paper really nailed it, at least for me. And similarly, at that around that time, there was the book Multivariate Calibration by Harold Martins and Tormod Ness from '89. That everything in that book was just extremely interesting for me, and I learned so much from that book. That there are probably better books today. Not that it's a bad book at all, but there's been developments also by those two authors, and they have written other books. But that book was just that made a huge impact on me. And sometimes when people think that chemometrics is just about PCA and PLS and maybe some design of experiments, I like to point out the handbook of chemometrics and qualimetrics that was written or edited by Massar and actually a lot of other people at the time. It is a very rich set of books. There's a lot of information there about how widespread and how many subjects are covered within chemometrics. I really enjoy that a lot. Um, what else? Simon de Jong is a Dutch chemometrician, and I would say I have enjoyed all the papers he's written. In my opinion, he's a very was a very insightful guy, and I enjoyed all his papers very much. And then when it comes to software, I will also reveal my age. I really like MATLAB. I've been using MATLAB from the very beginning. When I did my master project in, I have no idea, 93 or something, the internet wasn't really so present at that time, but there was something called Gopher, I believe. So that's pre-HTTP. And on Gopher, you could download a freeware software package called PLS Toolbox. So I got that, and I managed to manipulate some of the functions to make sort of alternative versions of PLS for some calibration modeling. And I've been working with the PLS toolbox ever since, and like it a lot. But mainly in MATLAB. MATLAB makes it so easy for me to be creative, so I enjoy that. I don't have anything against Python and R, but I've just been using MATLAB for 30 years. So for me, it's an extremely powerful tool.
Well, that's fantastic. Do you make some of your programs available to?
Yes. Yeah. Actually, we've been doing that since the very beginning. So back in the 90s, we were so fortunate that there was a guy in our group who was into IT and had a web server. So right from the beginning, we started making our software and data available. We didn't really have any particular reason for it. We just found it so interesting with this internet, and it turns out that it was a very good way to do quality control on your software, because if I have to put out, if I make a PLS algorithm myself and just make it for myself, maybe I will cheat a little bit and it's fine. But if I have to put it on the internet, I actually have to make sure that it works and that it works correctly. So it's a very good way to force yourself to be a little bit more structured than at least I want to be. It also turned out in the end that probably was a good way to sort of advertise our work, but that was not really the intention from the beginning. We just wanted to share everything, and ever since that time, we have tried to share all. I mean, every time I write a paper, I put the software on our homepage and the data if I'm allowed, and it really, really is a good way of building up collaboration, and it's a good way of getting other people to fix your problems, because if I put my data on the internet, then other people are going to make even nicer methods and even nicer tools for solving the problems I have, and so it's just a win-win. So I really, really enjoy that.
Well, thank you for sharing that. Um, can you tell us what scientific committees or groups are the best to be involved in related to chemometrics work?
Hmm. That's a good question, and I think maybe for many years I it's not that I try to avoid chemometricians at all. I definitely did. People will know that. But I try to go to non-chemometric conferences, because for me that was a very nice way to get inspiration. You know, going to other scientific communities, trying to understand what they were talking about, because they spoke in a different language. So I went to psychometric conferences, signal processing, linear algebra, all kinds of conferences. And for me, for many years, that was a great inspiration, and kind of an easy way to sound creative, because you learn from other scientific communities. Um, so I'm actually not sure I'm the best one to ask advice on committees and groups. We try to work with as many groups around the world. We always had a lot of visitors from all over the world, and so we believe that we have friends in most bigger chemometric groups, and we try to send our students out and to get visitors from those groups, and that is just it's a big inspiration to get people from other groups that come with other experiences. Um, yeah, so I apologize that maybe the advice is not so
Oh,
constructive.
that's a very unique way of looking at things, and it's worked very well for you. Um,
Mm.
that's interesting. You've contributed a lot in terms of published articles and book chapters on chemometrics, and we've listed some of those in the references and further reading sections in this podcast. Um, in your opinion, is there still anything lacking in either the available publications or modeling methods?
I no, I like the list. We do have. We recently started a new website. For technical reasons, we had problems with our old website, so there's now a new website of the Chemometric group, where we're gonna have most of our activities in the future. So I think we should add that to the list. And also, I would like to point out that we have a YouTube channel. Um, we are somewhat active on the YouTube channel. We have whole courses on different things like multi-way analysis, or basic chemometrics, how to build a calibration model, how to do pre-processing. And we also have something which I enjoy a lot, which is it's a set of YouTube videos called Monday webinars, where we get people from all around the world to give a presentation of something they're working on currently. And it was something that started during Corona, as is very normal, I guess. but I still like it. It's a good way of getting inspiration, and also you will see in that list some of it is very chemometric, but there's also stuff from completely other different fields, and it's one of the benefits, I guess, of Corona, that now the world is smaller in that sense, and we can have people give us a presentation every now and then. So that's something we try to expand on this thing, and it's run as a webinar, but then we save it on this YouTube channel, so you can go there and watch all of these. There's a lot of nice information.
Well, that's interesting. We'll make sure we get those listed in the podcast post. You published a paper describing a solution to a common problem which a lot of people face. They're using chemometrics and spectroscopy, and that's maintaining multiple complex calibrations over time. In this paper, you suggested a new approach for rationally merging calibration models in order to optimally balance the prediction error and the maintenance workload. Can you explain this approach a little bit?
Right. Yes. So many large companies are often running, maybe tens, sometimes hundreds, and I even heard of close to 1,000 different calibration models. So that could be 1,000 PLS models or neural network models or whatever. But each and every model, those who have tried to implement calibration models, for example, in production, knows that each and every model needs to be maintained. And that's work, that's real work for each and every one of them. So imagine that you have 20 models. It becomes cumbersome, and it becomes annoying, or at least time consuming, to maintain all these, and it's not really cost efficient, maybe. And what I've seen in several companies is that if you want to avoid that, solution number one is to merge everything into one model. And of course, if that works and the results are satisfactory, that's fine. But it's not done typically because it's, let's say, optimal. It's done because that's just the only thing you explore. So either you do 20 individual calibration models that you need to maintain, or you merge them all into one. And what you will find, well, it depends very much on your case, but what you will often find is that the merged model is going to be quite a bit worse than the individual models. So if you look at the error from the merged models compared to the 20 individual models, you paid a price for doing that. So what we did was that we developed an algorithm that will automatically take you from 20 through 19, 18, 17, etc., down to one model. So you get the whole path from what should I do if I wanted to have 12 models instead of 20, or if I wanted to have 5 models, etc. And what you often find, not always, but what you often find is that there's an optimum somewhere. So maybe actually you get better predictions by merging into 3 models, because now you get more data for those 3 models, and if the underlying samples are actually similar, then there's a benefit in the prediction error. And now you only have to maintain 3 models instead of 20 models, and clearly that's an advantage. So basically what we provided in that tool is a way to rationally and scientifically, whatever, go from 20 to 1 or 100 to 1, or whatever is the case, in a rational way, instead of just saying, okay, only alternative is one model. Now, sometimes you can actually deduce how you should merge, and often that works equally well. I take all the black models and put them together, and I take the orange models and I put them together, and that's actually gonna be a rational way to model. But sometimes it's not so clear, and sometimes it's not obvious what would be the right trade-off, and that this method can be really helpful.
Excellent. For our listeners, the title of that paper is Calibration Model Fusion, and it was published in the Journal of Chemometrics in 2021, and it's also in our references and further reading. All right. And you've published a paper describing how Parafac offers a very attractive approach for modeling fluorescent excitation emission matrices. Could you explain how this approach works and the advantages over other data analysis approaches?
Yeah, thanks. That's a nice question, especially for me, because that's probably what I spend most of my work life on, is Parafac. If I can start maybe by saying the reason I sort of got into that is due to the fact that when I started working at the university, we had a lot of projects with fluorescence. Because we wanted to investigate fluorescence as an alternative to NIR, near-infrared spectroscopy. And we were approaching that with PLS models, which is a classical approach for building spectral calibration models. But it felt a little frustrating since the fluorescence data that we measure, excitation emission, it's not really a spectrum per sample, but it's rather a matrix per sample. And so the data becomes a box, which is called a tensor or a multi-way array. So it always felt a little bit frustrating. And I knew about the concept of multi-way analysis, but I found it very complicated. But I knew that potentially it could be interesting. I struggled writing an algorithm, but I had a brilliant student who wrote an algorithm for a similar model, something called Tucker, and made me so mad that he was able to do that I finally decided I have to make a parafag algorithm. And so I managed finally, and it turned out that it was fantastic on fluorescence data, and it is fantastic because it allows you to do what I call virtual chromatography, and which is really what it is. You can measure fluorescence measurements on mixtures, and then you can resolve them just like you do in chromatography, but with parafag. So mathematically, you can separate the contributions. And it has exactly all the problems or issues that normal chromatography have. You don't get real absolute concentrations, you get relative concentrations, you get areas or similar or signal intensities, but it really has all the properties that chromatography has. And it just turns out that a lot of fluorescence data on relatively simple data will behave very, very nicely, and parafag therefore is able to give you the underlying excitation emission spectra for identification and the relative concentrations. And I would say that it has changed the way fluorescence data is analyzed in a number of fields, most spectacularly in environmental monitoring, where people are using fluorescence for monitoring dissolved organic matter. And before parafag, the handling of the data was less than impressive. But now I would say that parafag is the default there, and that's what everyone is doing. So I really think it became a game changer in certain ways of using fluorescence data.
Well, thank you. I'd also like to point out for our listeners that this is listed in the references and further reading sections. The title of the paper is E.E. Miser, Automated Modeling of Fluorescence EEM Data. And that was in Chemometrics and Intelligent Laboratory Systems. So thank you. That sounds remarkable. In another paper, and you've mentioned that already in our podcast here, is that you applied Parafac2 for GCMS data. We know that GCMS data can be really complex with overlapping retention time shifted, low signal to noise ratio peaks, etc. So what did you learn from this work, and what would you say are the advantages of using this approach?
You're right. Thanks. Yes, we have been working a lot on that for the last 10 years or so. And Parafac 2 was a method developed within psychometrics. It was actually developed in 1972 by a guy called Richard Hassman, a very visionary guy. He didn't know how to make an algorithm for it. He just wrote down the theory and said that's going to be interesting. And so for decades, no one actually knew how to analyze data with this algorithm, because there was no algorithm for computing it. But we found that later on in the early 90s, and it turns out that it just works remarkably well on GC data. So the problems you have with GC, especially untargeted GC, is that you have retention time shifts. That's one problem. You have low signal to noise. You have baseline. You have overlapping signals and stuff like that. And all of this can be handled by Parafac 2. So basically, Parafact 2 is like a PCA model, if you're familiar with principal component analysis. So it splits the signal into some underlying entities. And you can split the baseline from the peaks. You can split overlapping peaks as long as they're not completely overlapping. I mean, they can be completely overlapping, but they can't have the same shape, but they can actually be completely covered in each other, and you would still be able to recover that if the spectral differences are enough to separate them. And so it's a little bit similar to what we did on fluorescence data with Parafact. Then this Parafact 2 model can actually do something similar on the chromatographic data. And there, the gain is much more profound. A lot of fluorescence data on relatively simple samples is quite simple. You typically find that with the signal to noise ratio of a particular instrument, you find 5, 10, well, 10 would even be a high number of fluorophores in a data set of whatever, wine samples or something. But of course, in a GC data set, there's much more information. And also we find there's a lot more information that is hidden that we can't actually see with our bare eyes. But with Parafact 2, we can dig that out. Sometimes we are surprised by what we find in the baseline, where on hindsight, maybe we can see that there's something, but we never actually identified that there was something. But since Parafact 2 sort of, let's say conceptually, it averages over all the dimensions, over the retention time, over the spectral domain, over several samples, it actually provides a huge sort of signal to noise gain by doing that compared to many of the traditional methods. So we find that we can find more information, and actually also something which may not be totally acceptable to an analytical chemist, but we don't have limit of detection, in the sense that we quantify all compounds even when they are below limit of detection. So I'm not saying the concept of limit of detection doesn't exist, but I'm saying we quantify all of them, even those who are below. And that's important for us, because we're not doing analytical chemistry. We're using the concentrations as patterns in some kind of pattern recognition, like some kind of multivariate models. And we would like to quantify all compounds, also if they're below limit of detection. So limit of detection becomes a post thing. It's something you can decide on later if it's relevant to you. But for us, it's normally not relevant. And we would like to know the concentration, even if it's below limit of detection. So that's one nice aspect of this, I would say.
Following on the same topic, you have a well-known Parafact tutorial and applications paper. It has over 3,000 citations. And you use the terms multi-way case and two-way case and multi-way methods and unfolding methods. Could you explain a little bit about what those mean?
Right. Yeah. Thanks. So normally when you analyze data, traditionally you have a matrix of data, or you have an Excel sheet of data. So that's a table of data. Now, in our terminology, we call that a two-way data set, because there's two entries. Maybe you have an Excel sheet with different samples, so the rows would be different samples, and you measured some variables. That would be the columns. So you have a sample direction and you have a variable direction, and that we would call that a two-mode or two-way case, meaning a matrix. And the reason we use that is that we can then also generalize this. If you have several Excel sheets, that could be a multi-way case. So now I'm measuring on all the samples, I'm measuring these variables, but I'm doing it at time point 1, 2, 3, 4, which then becomes different sheets in the Excel sheet. And that would be a multi-way case. It's also nowadays, well, let me back up and say, these methods most of them were developed in psychometrics in the 60s and in the 70s. A lot of the pioneering work took place, and they often call them multi-way data. Later on in chemistry, we looked into the same things. In particular, the group of Bruce Kowalski in Seattle looked into this, and they call them tensor data. So a three-way array could also be called a third-order tensor. So that's another notation that might be a little bit confusing. Nowadays, multi-way analysis has spread into all kinds of data science and machine learning and AI. And in general, in most scientific fields, it's now referred to as tensorial data. So people would call it tensor data rather than multi-way data. But in chemistry, we are a little bit old-fashioned or historical, so we still prefer maybe the terms multi-way and two-way. Now, once you have extended, going from a matrix to a three-way array that's a big leap, perhaps. But once you have done that, it's very easy to go further on and say, well, I could measure this three-way array at different locations. That would give me a four-way array, or I could measure it using different chemical treatments. That would be a six-way array, seven-way array, etc. The extension to higher order data is not very complicated. The big conceptual difference is from 2 to 3, but also the big gain, I would say, is from 2 to 3. Certain things happen when you go from two-way data to three-way data, and a lot of the basic concepts that people who are skilled in linear algebra are used to, they suddenly don't apply anymore when you go to multi-way data. That's actually also one of the things that intrigued me initially. There were certain things that were unknown or mysterious, and actually they still are. Sort of like some concept of rank is very well established for matrices, but not at all so for three-way arrays. Now, if I let me continue and explain about the unfolding. So if you don't have the tools to analyze your three-way data directly, which is often the case because in many available tools for analyzing data, you don't have that availability, then you need a way to rearrange your data into a matrix such that you can actually analyze it with more traditional tools, because almost all traditional tools in data science are based on matrices, on two-way arrays, and therefore you need to have a way of turning your three-way or nine-way array into a matrix, and unfolding does that. It's also more recently been named matricization, which sounds a little bit terrible, but those of you who know something about linear algebra knows that there's something called vectorization, and matricization is a similar term, where you simply rearrange your three-way array in such a way that you can now present it as a matrix. You basically put the Excel sheets next to each other, and then you have unfolded your data to a very long Excel sheet that you can now analyze with traditional methods. Now, in many cases, you would be more susceptible to noise, so you would find that whatever you're estimating would be more noisy. But there's also some cases where you really need to do that in order for things to be meaningful. So, for example, images are often multi-way arrays. If you look at a normal JPEG image, you can see that as XY coordinates, and then RGB, which is a free channel sort of spectral mode. So that's a three-way array, but most three-way methods wouldn't actually work extremely well on that, and you would probably prefer to unfold it to a matrix and analyze it with matrix methods.
Huh. That's fascinating. Well, in closing, Rasmus, what would you tell our audience is the big secret of applying chemometrics?
That's a good question. I think the trick in chemometrics is chemo. And I really, really think that is what defines us. And it has always been historically. Svan de Waal, one of, the guy who developed the whole field, was always very strict on the fact that we should remain close to chemistry. And I do believe that. I do believe that what is special about us is that we know the chemistry. We should develop, and we should steal from statistics, from machine learning, from AI, from computer science, from signal processing, from filtering, from time series analysis. All of that belongs to us, but we combine it with our chemical understanding, and that's what makes a difference. We use that actively when we analyze the data. So I think the big secret is understand your data and understand all of it. Understand how it was sampled, understand how the measurements were done, understand how they were, what's the quality, etc. We have a tendency to, we like that the samples are measured by a laboratory with a fancy name from France, because then it's probably fine. But it's not fine. You actually have to go in and take sort of control and make sure that all the data is meaningful to your context. So understanding data, I would say, is the big secret.
Oh, excellent. Well, thank you, Rasmus, for this extremely informative discussion on your work. I'm sure our audience has learned a lot about advancing and automating chemometrics for analysis of chemical data, and your thoughts on this subject have been extremely illuminating. My thanks to all of our listeners and production and editing team that has worked to make this podcast possible. We invite our podcast audience to stay tuned to our next informative Analytically Speaking episode. And remember what Albert Einstein once said, it's not that I'm so smart, it's just that I stay with problems longer.